Hello, everybody. Last week we started talking about visual motion. Our purpose with this chapter is to use motion information to get more data about the scene. The motion could be caused by the camera motion or the motion of the objects in the scene. Most of the time, it doesn't matter which one is which. If the algorithm that we are studying is sensitive to what type of motion we have, of course we will tell you about that. Okay, so last time we talked about how motion is useful for getting the 3D structure of the scenes or for recognition. We talked about those, and as an introductory um, example to see how motion is useful, we are going to look at this problem of time to collision. In this example, I have a camera looking at a scene, and I have an object. Let's say I have a circular object. This object is approaching to the camera with a speed of v0. Okay, it's a constant speed, and if I know that the distance between camera and the object is L, I know that it would take me L over V0 seconds for the collision. Okay, so I know the time to collision for now. The thing is that in the real world, it is difficult to know the distance of the objects to the camera, or it is difficult to know how fast they are towards the camera. So getting these two values from the real world is difficult. I mean, can we do something else? Can we use the images that I am capturing with this camera to find the time to collision? That's what we are going to look at for now. Okay, so just simplify the problem. Let's look at, instead of three-dimensional world, let's look at the two-dimensional world. Okay, this is our camera. This is our center of projection. Our focal length is f. Our object is, since our objects are now one-dimensional objects, our object is L high. Okay, this height is L. Okay, and this object is approaching our camera at a speed of v. Okay, so if this object, whose size is L, is imaged by this camera, then let's look at this triangle here. Let's look at this triangle. Use red. Okay, this triangle here, and this is the height of our object on our image plane. So there is this similarity of the triangles in this example. What are the similarity of the triangles? If the distance of the object is d0, okay, so d0 over f is this distance, so this d0 is here, this is d0, and this is d0, this is f. d0 over f is equal to L over okay, I think I am back. Okay, let me make sure that I am okay. Connect this again. You guys hearing me okay?
Yes.
Let me, just a minute. Let me make it more reliable. Okay, now, so this triangle again, if I do the triangle similarity equation, d0 over f is equal to L over LT. LT is this LT is the height of the object on my image depending on the time. Okay, LT is from that way. So L, what is L? What is L0? Tell me L0. What is L0? What is L0? L0 is just, I think it is this one, right? Did I write it? Okay, I think it is L0. This one is L0, right? This one is L0. L0 is just F times L over D0. If I write this depending on the, okay, at time 0, my object is D0 away, and the size of my object on my image is L0. Okay, but if I say, let's say I am writing my dt depending on the time. What is dt? d0 is d0. Yeah, I know that. dt is d0 minus v times t. V is the speed of the object that is coming towards the camera. T is the time. So in this case, if I write LT is equal to F times L over D0 minus VT, right? So that's what I know. Okay, that's what I know. I can write that. But to calculate the time to crash, all I need is this d0 value and the v value. Okay, so d0 is at the beginning how far away this object is, and v is the speed of the object. So if I know these two, I can calculate the time to crash. So, but I like to do more than that. I like to do something that uses the image of the object that I am looking at, and I like to use motion. This one didn't use any motion. This one say that if I know the speed of the object and the initial distance of the object, I can calculate this. I like to use the speed of the object. Okay, I like to use the speed of the object. Maybe I could use this one. Maybe I can say I am writing this. The height of the object changes with respect to time, and if I take the derivative of both sides, maybe I can do some stuff, right? I'm going to do it that way. By the way, let's go to this. Can I sell? Okay, copy. There is a YouTube video. Let's look at that video. I am going to paste that video address to you so that if you don't see it properly on my screen, you can play it yourself. Here it is. You might wonder where we are going to use such a thing. It is useful to make these kind of time to crash, time to collision calculations. I have a setup. There is a ping pong ball on a glass, and okay, this is the setup. As you see in this setup, I don't know what happened. Should I reload again? I'm going to quit from the browser, load it again. I am guessing you are already viewing this video on your browsers already. So this is the view on your upper right. This is the view of the setup. There is a camera here. It is looking upwards, from down upwards. Okay. This is the view of the camera. Okay. This camera sees the ball. The ball is moving towards the camera. Okay. It is doing the half transform circle detection. When it does the half transform circle detection, it knows the object height, right? The L. Okay. If it knows the speed of the object, and if it knows how high it is, it knows when it is going to hit this glass. But we don't know any of those. All we have is the motion information. All we have is the motion information. Like this, if I look at the next frame, I am going frame by frame. As you see, the ball is moving towards the glass, and the ball is getting larger and larger, and the height of the object is getting larger and larger, and I'm supposed to calculate the time to collision. So these kind of things are common. These kind of things are common in real life, and you need to do it in a very, very fast way. That's what I'm going to do. But as we said, in this case, I don't know the D0 and V. So how should I calculate the how should I calculate the T value without knowing these two? Okay, that's what I'm going to do now. This is something that we already know. Okay, dl is equal to f times L over dt. We already did that, right? Why? Because we said that LT over L is equal to F over dt, right? That's what we said. Okay, so this equation is same as this one. So up to now, in this course we took lots of derivative operations. We took lots of derivatives of many expressions, but most of the time those derivatives were with respect to image x and y components. Now we are going to take derivative with respect to time. Okay, we have never done this before. Now we are going to do that. Let's take the derivative of this thing, which is equal to f times L times dt, right? Okay, so let's take the derivative of these two things at the same time. So how we are going to do that? L t over dt is equal to f and L are constants. They don't depend L, right? They don't depend on L. F and L are constants. So what am I going to do? I am going to do this f times L times d2 to minus 2 t minus times okay, I am going to put this minus at the beginning. Okay, minus 1 over dt, okay, like that. Okay, I forgot to d here, so this is a d. Okay, maybe I should write this in a more clear way. Make it like that. D dt over dt. Okay, good.
The derivative is, I think, on the denominator, on the upper side, I think. Because
you mean what? Okay, this is d to the minus 1. If I take the derivative of it, minus 2, I put it in there, and I am taking the derivative of this one, and I don't know how to take the derivative of, because it's a function, right? I am taking the derivative of this function, and instead of taking the derivative, I write this expression, and I don't know how to take the derivative of this one either. Okay, so let's look at this equation. This equation is telling me that, okay, what is this? Can you tell me what this is?
We have a function d, and we want to derive it with t parameter, but because of we don't know d function.
But what is the function? D function. What is the function? The function is the distance of the object away from the camera, right? It's the distance of the object. If you take the distance of an object with respect to time, that means speed, right? Speed of the object. Is that true?
Yes.
That's the speed of the object. And in fact, I think we have written this. I think we wrote something like that. We say that dt is d0 minus vt, right? That was the function for dt. I think I wrote this somewhere. Yeah, okay, here it is. This is what dt is. If I take the derivative of dt with respect to t, what would you get? dt over dt, okay? So you will say this is a constant, so this is 0 minus okay, minus, if I take the derivative of this thing, v times t over dt, okay, it is just v. So dt over dt is just minus v, okay. So I can put minus v in here, right? This would be a minus v, right? So I could say this part is equal to f times L over d square t times v. I can do that. And this minus v and this minus cancel each other. How about this one? What is this? dLt over dt. What is dl? Okay, what is lt? What is this? What is L? Tell me what L is. What is L?
L is the length of object on our image.
Yeah. No. L is the height of the object in the real world. This L. This LT is the height of the object on our image. Remember, this is the picture, okay? This is LT. L is the height of the object in the real world. LT is the height of the object in our image, okay? So what do I get in here? It is, this one is the speed of the object, maybe, yeah. It is just small v, okay? Speed of the object on our image. This is large V, capital V, and this is the speed of the object on our image, okay? So I did something, I don't know what I did, but I did something. Now I am talking about the speed of the object, the distance of the object, height of the object, focal length of the camera, and the speed of the object on our image, okay? We never talked about anything like this before, because if you take the derivative of okay, objects on the images, then you are going to get the speeds of the object, and this value and this value are very, very different, okay? This value is a three-dimensional speed. This is just two-dimensional speed. Since in our example this is a two-dimensional, this is a one-dimensional, this is a two-dimensional speed, this is just a one-dimensional, very simple speed. This is just how fast the object is getting larger on the image, okay? This is how fast the object is getting closer to the camera. So by looking at this equation, I am not in a better place than where I started, because in where I started, I had this initial distance over v. Now I have all this crap, okay? I think the book does it better. If I take the derivative of this LT with respect to time and multiply with this one, I get this. Okay, so
in this equation, dt is on top.
you are saying this? What did I do?
Yeah,
I put this minus one in here. Yeah, that's true. That's true, because I didn't have. Yeah, I shouldn't have this one. I think I should have. Good. Because this is dt, I should take the derivative of t, and the v should be here, and this is a capital V. And so what you were saying, correct. So the derivative of LT with respect to t is equal to this one. So f times L times d1 over dt, and if I take the derivative of it, Okay, like this one. So this one is going to be minus v, and I'm going to see it. So, but when I look at this one, I don't see anything. I don't see anything simpler, because previously I had t value as d0 over v. Now I don't see any t value. But if we continue, let's continue. Okay, I have this equation going from this. Now I can write this. The derivative of L with respect to time is okay, the real object speed over d square t times f times L. Okay, so I don't see anything new. But if I write this, let me write this. Let's remember this one again. Lt is equal to what? Lt is, do you remember what Lt is? F times
Big L.
L over dt, right? F times L times 1 over dt. Okay, so I have this and I have this. Maybe I can divide this side with this side and this side with this side. What would I get? If I divide both sides, let's divide it, and divide it equals, right? So L prime t over L t is equal to, come on, okay, make it smaller so that I can fit in, is equal to what? You tell me. This part would cancel it, would cancel each other, right? And in the upper part I have v. In the lower part I am dividing this with this one. It would be dt, right? That's what I would get, dt. So just talk about this. What is v over dt? What is v over dt? My object is approaching towards me at 10 meters per second. Okay, and my object is 10 meters away. You understand? Okay, what is v over dt?
Eşittir VT in speed calculation. It's time.
It is just opposite of time, right? This is what is v. V is distance over time, and if I do just the opposite, t is equal to d over v, and 1 over t is v over d, right? That's what I'm doing. So then in this case this will be equal to 1 over t. So if I somehow can calculate Lt over L prime t, I would get time to collision. What is Lt? Lt is the height of the object on my image. What is L prime t? What is L prime t? L prime t is the derivative of the height of the object on my image. How would you calculate this derivative? Okay, how would you calculate this one?
It's the derivative of ln lt. So if we take integral, it will be ln lt.
You are taking the integral to calculate the derivative?
This is, yes, because this is derivative of ln lt. So
You don't, no, you don't have to. This is much simpler. Look at this one, okay? This is my image. Remember that ball in the first frame, let's say frame number 1, the ball is like this, and frame number 2, the ball is like that, smaller. Okay? So the height of the object is, let's say, 10 pixels. Now the height of the object is, let's say, 8 pixels. So what would be the L prime T? I would say 10 minus 8 over just 1. It's just 2. So every frame, my object is getting 2 pixels smaller. That's the speed, okay? That's the derivative of my object's height. I'm taking remember how did we take the derivative of a image with respect to x? How did we do that? We said that we would take ixy minus teşekkürler. I would take ixy and I would say x minus 1y. Okay, so I am just making this calculation with respect to these two neighbors on the horizontal line. If I am taking this with respect to x, if I am taking the derivative with respect to y, I am going to do it with respect to 2 pixels in the vertical neighborhood. But now I am taking the derivative with respect to t. Okay, with respect to t. But in that case, the height of the object at this time and height of the object at this time. And if I subtract this one from this one and divide it to the time interval, I am assuming just 1 unit of time. Okay, and it's going to be just 2. That's what you do. So all I am saying here is that calculating this L prime t is not difficult. You just measure the height of the object in 2 images. Okay, you just measure the height of the object in 2 images and take the difference. That would be your derivative. What is this? This is just the height of the object, right? So you divide the height of the object to its derivative with respect to time. That's going to give you the time to collision. That's going to give you the time to collision. Okay? So I think, yeah. So this is the equation for the derivative of L with respect to t. This is just L, equation L. And if we take the ratio, we would get this. Time to collision. Previously, time to collision was we need to know the d0 and we need to know the speed of the object itself. Okay, now we don't have to know both of them, none of them. Okay, we don't have to know none of them. By simply dividing this value with this value, I can calculate them without knowing this value or this value or d0 value. All the measurements are done on the image of the object itself. That's it. That's it. So if you go back to this, example again, by looking at the change of the size of the object, I can make these calculations. But there is only one case though. The speed of this object is not constant because it is moving under the influence of the gravity. There is an acceleration, right? A. So the speed of the object is not constant. But I think we can figure out something for this. Okay, so I don't have to know the size of the object. I don't have to know the speed of the object. I can make these kind of calculations in when should I expect the collision to occur. When should I expect the collision to occur? Okay, so all we are saying with these calculations is that it's a very simple calculation. Time is important, motion is very important. We should use motion information carefully, and it's going to produce lots of useful information for us. Okay, so the new thing that we did today, we used this idea of taking the derivative with respect to time. Previously, we never did that before. We take the derivatives of with respect to x and y. We took two derivatives with respect to x and y. Second derivatives, okay, in edge detection, corner detection, feature point detection, etc. Now, since we have many images of the same scene, we can take derivatives with respect to time. And that's going to give lots of information for us, if you have it. Okay, any questions? Any questions so far? Okay, if you don't have any questions, I will just continue. This is what I said already. Time to collision can be found without knowing L, D0 or V. Okay, so you might say that this is very similar to stereo or multi-view geometry. Why? Because in multi-view geometry, we had two images, left image and right image, and these two images are separated by a baseline. Okay, we established the stereo between these two, fundamental matrix and etc. And we do our calculations, and we can calculate the depths of objects with respect to camera. That's what we did, right? That's what we did. Now, instead of having just two images, we have many images of the same scene, okay? And the images are taken at different times. So it looks like if our camera is moving slowly, every time we take an image of the scene, okay, we are taking another image of the scene and we are creating a multi-view geometry, you might say. In a way, this is true, but there are many differences. Why? Because in stereo, we assume that these two images are taken at the same time, right? In stereo, we assume that these two images are taken at the same time. In this case, we don't do that assumption anymore. So, what is the how does this affect us in our calculations? That means that our camera has moved. That's one thing. Also, the objects in the scene can move too. So the difference between the images of the motion of n frames might be because the camera movement, also the object movement. Okay, so the motion disparities can be due to scene motion or the camera motion. Okay, so there can be more than one transformation between the frames. In this case, we say that between the frames, there is a rotation and translation. That was it. That's why we said that using rotation and translation, we can calculate the essential matrix, no problem. But with the motion, R and T is not that simple, because there is R and T of the cameras, and there might be R and T of the objects too. Okay, so the motion is more complicated. Okay, and let's continue comparing the motion of comparing the multi-view geometry, namely stereo, and the motion problem. Okay, the correspondence problem, we need to track the corresponding elements across frames. Okay, we know that in stereo, correspondence problem is simplified because of the epipolar geometry, right? There is this epipolar lines. When we make a search in the other image, we need to make a search on the epipolar lines, because there is only one rotation and translation between two images. by doing this k minus 1 and then rotation translation k minus 1 of the other camera, I can come up with the fundamental matrix. But now I cannot do that because correspondence problem has to be more complicated. I need to make a two-dimensional search because epipolar geometry is not valid anymore. Why? Because the objects can move too. Okay. When we do the reconstruction problem in stereo, what is the meaning of reconstruction in stereo? To estimate the depths of each point, right? Depths of each point. That was the estimation of the reconstruction in stereo. In motion, it is a little bit different. It is more complicated. Okay? If you do the correspondence problem in stereo, you can estimate the depth. If you do the correspondence problem in motion, you are supposed to find the depth of each point plus the camera parameters plus the camera motion. Okay? So you are supposed to produce the depth of each point plus the camera motion for each point, or motion for each point. Okay, so this is more complicated. You are not just recovering just simple depths, you are recovering the motions of objects too. And then there is the segmentation problem. What's the segmentation problem of motion? We would say that in this scene that we are looking at, after doing the motion analysis problem, we are saying that what parts of the image is moving with each other and what parts are moving differently. I have a scene, I have another scene of the same environment. I have an object here, object A. Now object A moved here, object B, it moved there. Okay. Because of the camera motion, there is this disparity. Because of the object motion, there is another disparity. So if some of the pixels are moving together, then that's a good opportunity for us to segment it. So you would say that, okay, this is one segment of the image, and this is another segment of the image, and then maybe the rest of it is another segment of the image. Okay, so there is the segmentation problem. What are the regions of image plane which correspond to different moving objects? We did not have this problem before in this stereo. So overall, what I am saying here is that when you do the motion analysis of scenes like this, okay, it is more complicated because you need to find the correspondence without the help of the epipolar geometry. That's one thing. After that, when you are doing the reconstruction, you need to reconstruct the depths of the objects, okay, and the motion of the objects. That's the second thing. And then there's the segmentation problem, making a calculation to decide which parts of the image is moving together. Okay, so overall it is more difficult than stereo, but it is more rewarding too. You get more data out of your motion analysis. Okay, just one simple example here is that by making this simple calculation, I would know in what time, in how many seconds that object is going to hit me. Okay, if I am a robot, if I am moving towards a wall at a constant speed, it is very easy for me to know that in how many seconds I am going to hit that wall by just making this simple calculation. When, as a human being, if somebody throws me a ball towards my face, okay, it's a reflex that I do this, or I close my eyes, try to protect my eyes, or try to protect my face, and it is automatic. Why is that so? It's because it is so easy to calculate this one. I mean, the rate of the object growth is going to tell me if that object is going to hit me in a very short amount of time. My brain is not involved at all. It's just a very simple calculation. it is done much early phases of the brain processing, because it's such a simple problem. Okay, and it is done only by the motion of the objects. Okay, motion of the objects. Good. Any questions so far? Any questions? Okay. If there are no questions, then as I said before, we will do these kind of analysis and expect similar stuff that we did with the stereo. Of course, since we have the time, I need to take care of the time. I am going to take lots of derivatives, but this time I am going to take the derivatives both with respect to x, y, and t. So you will see, if this is my image, okay, I will take the derivatives of this images with respect to x, y, and with respect to t. Okay, so this might look a little bit more complicated, but it is not actually. The same ideas will be applied. For the correspondence between two motion frames, okay, like we did with the stereo, there are two methods: the differential methods, okay, that will correspond to our correlation-based methods. So that will give us a dense measure of correspondence between frames, okay. And there is this matching methods, that those are the sparse measures, and we did that too with the edges and the sift operators, etc. So there will be two methods. This one is going to be very different from the stereo though, okay, because in motion the baselines are very small. You don't move the camera like 10 centimeters to create a baseline at that for each frame. Your frames are very similar to each other, okay. Your frames are very similar to each other. If I go back here, if I go back this one, and if I move just a single frame, so as you see, the object is overlapping. When the object is even slower, see, it just overlaps. The difference between these two frames are, in fact, it was the same, is it? Yeah. So as you see, it is very similar, and I don't see this upper right circle is changing at all. So the difference is very small. If the difference is very small, then finding the correspondence is going to be difficult. It's like very small baseline. And in fact, there is no baseline at all. So I am going to try a different technique for measuring the correspondence between those images. Okay. For the matching methods, again, I am going to do that kind of stuff. For the reconstruction, that is the reconstructing the object positions x and y and depth, plus the camera motion, I need to take care of all these parameters. Again, the reconstruction and correspondence, which one is going to be done first is a problem. If somebody reconstructs the segmentation stuff, it's saying that these pixels are moving together, they are the same object, then my job would be easier. But to get that information, I need to find the correspondence first. So which one is going to be done first? First matching, then the reconstruction or matching. So that's a motion segmentation chicken egg problem. Previously with the stereo, of course, it is the correspondence first, then the reconstruction. Now I cannot make a decision on it. Usually we try to solve these two problems together. So as I said again, I'm maybe repeating this for the third or fourth time. Motion is more difficult than stereo, multi-view geometry, but when you solve the problems, it is more rewarding. Okay, you are going to get much more from motion than you would get from stereo. Okay, so it looks like I'm out of time. Let's take 10 minutes of break. Let's be here around 14:22. 10 minutes. Alo, merhaba Şaban. Şükür vallahi iyilik, sağlık, senden ne haber? Allah razı olsun, sağ olasın Şaban. Ne yapacağım aslında? Hayat ha geçen sene oldu onlar ya, evet. Evet. Valla işte bilmiyoruz ki ya, o kadar çok böyle etraftan haber geliyor ki kötü ötü şuraya buraya karıştırır yani.
çıkaramaz. Onun olması yok da. Doktor şey yapmasın.
Hocam bu sizin öğrenciniz Mahmut Can var. Evet. Kendisi gelemedi de bilmiyorum size mail attı mı? Şey var hocam doktoraya terbiye girecekmiş.
Evet. Ya sana gönderelim.
Ben size mail aldım. Bunları Nermin Hanım'a bırakıyoruz ama hocam.
Bilmiyorum ki herhalde ya. Ama şey hocada var. Nedir? Erdoğan Hoca'da bunun gireceği bilgisi vardı, bana gönderdi. Bunlara gerek yok değil mi? Tamam.
Yok hocam onlar öğrenci işleri için çıkarmış.
Tamam. Şurası kim imzalayacak? Ben buraya yazdım sadece.
Evet.
Bu kadar. Şunlara para atmama gerek yok herhalde. Yok.
Yok hocam onlar zaten
Tamam.
çok iyi eder.
Standart.
Teşekkür ederim.
Sağ olun. Görüşürüz. Okay, people, let's continue our discussion of the motion. With the motion, there will be some interesting stuff that we have never seen before. For example, the motion field. Okay, previously we did this. Previously, what we did was we take, and again, simplified real world. This is our camera. Let's say this is our object A. Where do I see this point A on my image? I would do this. Okay, this would be my point A on my image, right? That's it. And I have nice equations that comes from the similarity of the triangles and everything. With the motion, of course I have this, but I have stuff like this. If this point is moving, like this, okay, from here to there, then maybe I would say, okay, it's going to move from A to A prime, so this one is going to move A to A prime. So there will be a motion like this, a small motion, okay? It is not easy to see this vector on my images because there is no motion marks on single frames, right? All I have the single frames. You would have either the image of A or image of A prime. You don't have both of them at the same time on your images, so they all have to be calculated. And most of time I will lose lots of information when I take these kind of images. For example, this green arrow is moving both downwards and away from the camera, but I can have only a one-dimensional vector on my image. Okay, and if this green arrow is moving like this, then you won't see anything on this image. You won't see any difference on this image. So that will be a little bit different. That will be a little bit more difficult, but we will have to all handle it. Okay, so let's make a definition in the light of these concepts. The motion field. Okay, the motion field assigns a velocity vector for each pixel in the image. Okay, if you have a frame of sequences of a scene, okay, sequences of frames of a scene, how the frame changes, how the object changes, to represent that we have motion field. Okay, if this is your real v vector, the speed of your real object in three-dimensional world, three-dimensional v vector, you are going to have a v vector, two-dimensional v vector corresponding on your image. Okay, so in a way that this v is the projection of this capital V on our image. That's called the motion field. Okay, so the motion field can be thought as the projection of the 3D velocities on the image plane. 3D velocities on the image plane. Okay, so that's a new thing again, motion field. And we will come back to this motion field again and again. We like to estimate this motion field very precisely. Unfortunately, we won't be able to do that because estimating the motion field for general type of scenes is not that easy. Why it is not easy? We will see. You will see it is not that easy, and you will see why. But we will not give up, of course. We will do whatever we can do. We are going to estimate it up to some precision point. Okay, and we keep doing this. We kept doing this over and over again since the beginning of the semester. We say that there is a point P in the real world, and the projection of that P is here, and so what? And we know that if I multiply that P with an F and divide it by Z, I would get this two-dimensional point P. Okay, this is what we did since the beginning of the semester using the pinhole camera equation. We like this one. Now it is time to take the derivative of both of these points, okay, both of these sides with respect to time. When you take the derivative of the points, okay, or the equation with respect to time, you introduce the concept of speed, okay, v, velocity, okay. You introduce the concept of velocity like this one, okay. So somebody is taking the derivatives of these points with respect to time, their motion, both on the real world and both on the images, and they are getting those velocities, and I'm going to reach to those velocities using these equations. If you take the derivative of this equation with respect to t, from this one, what is dp over dt? It is the object's speed in three-dimensional world, right? The df over dt is, of course, it is constant, but dz over dt is different, right? dz over dz so dz over dt is not constant because z changes, z of the object changes with respect to time. It is different. So let's take the derivative of both sides and let's see what is going on in a few minutes. But before that, as we always do, if we are going to use a math theorem, math model, physics model, we introduce you the idea. Maybe you remember this from your physics course, physics 2, I guess, maybe the physics one, I don't know. Okay, the velocity and acceleration of a point A on a body undergoing general planar motion is equal to the translation of a reference point B plus the rotation of point A around the reference point B. I have 2 points B and A. Okay, they are moving, but they are not moving under the same forces. There is a relative movement between these two. Okay, if you take a standard real world coordinate system, they are both moving with respect to this O. But I am trying to find an equation that is relative between these two. So it has 2 parts. One is I can get VA. The velocity of A by using the velocity of B using 2 components. One of them is the translational component. Okay, so there is this VB moving in a translational component, and there is this rotational component, omega. Okay, omega and VB. Okay, VB is like it has 3 meters per second in X component, 0.1 meters per second in Y component, and 0 meters per second in Z component. It's something like that. Okay, this is a direct translational component of the relative speed between A and B. Omega is a little bit different. I cannot write on. Okay, I'm going to write W, and you are going to assume that that's an omega. Okay, omega is rotational. Okay, omega is rotational. Pi over 2 rotations per second in X around X, pi over 8 around Y, and maybe minus pi per second around Z. So these are rotational components. So you are talking about how fast you are rotating around each axis. Okay, so I have two components of speed between A and B, and to get this absolute speed between those two, relative speed between those two, A and B, translational component plus this component, but this component is this component, this omega component is cross product. There is a cross product between the omega and the distance between these two. Okay, if I get far away from the object, if the distance is far away from the object, this r distance, okay, this is the r distance between A and B, the effect of this omega is more. Okay, this effect of omega is more. Even the slightest omega value will introduce loss of relative velocity between these two objects. So the important thing for me here is that for point B, I am going to take it as a camera. Point A is going to be the scene point. So important thing here is for me, what is the relative motion between the camera and the scene? Okay, and that motion is going to have two components, translational component and rotational component. Okay, so what is r then in that case? R is the position of that point, of course, because in camera coordinate system this point is 0, 0, 0. That r corresponds to the point position, right? So this is going to be the point position. This is going to be the rotational component, and this is the translational component. Okay, exactly what I am saying here. So the relative velocity of P with respect to camera is translational velocity and rotational velocity cross product by P. Because we are using the relative velocity, we are using these minus signs here. Okay, instead of moving objects like that, assume that we are moving the camera in the other direction. That's what we are doing. Okay, so if the motion is like that between our camera and the scene, relative motion, it will have two components, translational velocity and the rotational velocity. This translational velocity and rotational velocity is very similar to stereo baseline. Okay, remember with the stereo, between the cameras I have the R and I have the T, right? I have R and I have T. If you remember, to get the essential matrix, I multiplied R and T using the cross product. This something similar is happening here. Something similar is happening here. So what we said, stereo and motion are similar. Motion is a little bit more complicated, but they are similar. And this T and omega is omega kind of corresponds to R, rotation. Okay, this translational component kind of corresponds to the baseline distance between the two stereo pairs. Okay, so let's keep this in mind. Let's keep this in mind, and we will come back to this when we take derivative of these two sides. From this side, with respect to t, the speed of the object will come. Okay, and if we take the derivative of the small p, the speed of the velocity of the object on the image will come. Okay, so this one is of course this is a three-dimensional world. It has x, y, z components, both of them, omega x, omega y, omega z components, and p has three components. And if we write this as three separate equations, of course I will have to do that. Omega has three components, cross product by x, y, z. I get this equation, and this equation. Do you remember how to do the cross product between these two three-dimensional vectors? We write the skew symmetric matrices. P is a three-dimensional vector. Px, Py, Pz. Omega is a three-dimensional vector, but I am going to write it as a skew symmetric matrix. How do you write a skew symmetric matrix? You would put 0, 0, 0. Then you do what? Do you remember? You say this is
Like
omega x, omega y, omega z. Then this is symmetric, right? Omega y and omega x. And I put minus, minus, and minus here. It's not perfectly symmetric. It is skew symmetric. If I do this matrix multiplication, this is a matrix multiplication now. 0 times px minus omega z times py minus omega y times pz. That would be the first component of this vector. That's what I do, right? Okay. So 0 times px minus omega y times z, okay, this z, plus omega z times y. There is a minus here. That's what I get, the minus. And this is the y component. This is the z component. Okay. These are our speed vectors. And if I divide my speed vector into two, translational part and the rotational part, this is what I get. Again, these three equations, we did not talk anything about images. These are all in the real world. Okay, these are all in the real world, and these equations are between the objects in the real world and the camera in the real world. We did not talk about the image points yet. To talk about the image points, I need to use this equation, similarity of the triangles. F times P over Z equals P. Okay. Here I have the XYZ components of the P. Okay, here. And then when I take the derivative with respect to P, I will get the Vx, Vy, and Vz. And that's how I am going to connect these equations with the with the image points, speeds of the image points, velocities of the image points. Okay, any questions up to now? Any questions up to now? Okay, let me continue then. Like I said before, I'm going to take the derivative of these two, this equation, left side and right side. And let's take the derivative. Salman is going to help me in here. So let's write P is equal to F times P times Z minus 1. Okay, let's take the derivative. dP over dt is equal to, F is a constant, right? And so this one is dependent on T, and this one is dependent on P, right? So let's take the F. How do I do that? dP dt times z to the minus 1 plus P times z to the minus 2, right? And then dz dt. Salman, check the math. Is this correct? Is it right?
I think there should be minus.
Oh yeah, there's a minus. There should be a minus in here, right? This should be a minus, right? What? Because there is this minus 1 there, right? Is that true? No? Is that? Yeah, because it is, yeah, over 2. Okay, so this is what I did. And let's look at this one. This one is F times, this is V, right? The speed of the object in real world. Speed of the object in real world, this is Z minus P over Z square times, what is this? This is the speed of the object, but speed of the object in Z dimension only. Vz is equal to the velocity of the point on our image. Looks like these two parentheses should be like that. Okay, so if I rearrange this equation, and I know that this is a three-dimensional vector. This is a three-dimensional vector, right? And this one is just a scalar because the z component of this v. I know that there are three equations in this equation because this one is a vector. Let me mark the vectors with this one. It's a vector. This is not a vector. And this one is a vector too. It has x component, y component, and z component is 0 because nothing is changing with the z component. Okay, so I can write these three together, and this is doing exactly the same thing as I do, but I think it is putting it. It is isolating this z square like that one. Okay, it says that f over z square times v times z, okay, minus p times vz. So I am going to use this equation. To substitute back these because I have x, y, and z components. Here I have x, y, and z components. If I put them together, I am going to get a set of equations. Vz is going to be 0. Why? Because on your image plane there is no z speed, there is no z velocity. Okay, Vz is going to be 0. I am losing any speed about z. Okay, I have only Vx and Vy, small v, small y. In real world, of course, there is Vz, different. It might be different from 0, negative or positive. Okay, let's put this Vx, Vz from this equation, and we are going to get this. Well, it might look a little bit complicated, but it is not actually. It is not. Why? Because all I did was instead of Vx, I substituted it with this equation. For Vz, I substituted with this one. I ended up using this. What does these two equations tell us? It tells us that your velocity on the image depends on your Your depth, that's good, right? Your depth, how far away you are from the camera. Focal length of the camera, here. Your velocity in x, okay, your velocity, your relative velocity in x and z dimensions. Also your rotational velocity in y, z, and x. Well, this is interesting. What is this? And I have this one. Wx, xy, and x squared. Where did I get those? Okay, I got these from there, right? X and y. Right? This is x and y. And I get all these, right? Oh, okay, I missed telling you this one. I get this one, right? I get this one. And f over z squared, this one, and instead of this capital P, I wrote this one. Remember, this is main equation from the beginning of the semester. I wrote this one. So this is P times Vz over Z. So P is image point. P is image point. So your velocity on the image depends on your real world velocity, real world depth, okay, and your velocity in the z dimension. Okay, this is interesting, right? Tell me what you see as tell me what you see as interesting in this picture, in this equation. Your velocity on the image depends on the camera focal length. Your speed in the real world, yes, and your image coordinates on the image. But it doesn't depend on what? Something interesting. It is interesting that my velocity on the image does not depend on the what?
I don't know if I'm correct, but it doesn't depend on x and y axis of boundary.
Exactly, px and py, right? It depends on pz. Here it is z, but it doesn't depend on x and y coordinates. It is interesting, right? It is definitely, it depends on z. It definitely depends on vz, of course, because vz is here and vz, and p is there. How can you say that? Of course, maybe we could say this. Since p depends on px and py, right? This information is already contained inside this p, right? Inside this p. That's why I can write this. It's interesting. So when I plug everything in, that's why I get these. And if we look at this side, this is an interesting side actually. We like to think about this side and about this side separately. We like to keep them differently. Okay, we like to keep them differently because they talk about the different stuff. For example, if there is an omega, it doesn't talk anything about it doesn't talk anything about depth of the object, right? It has nothing to do with the depth. All it has to do is the x and y positions of the object on the image. Okay, so that will tell us something. It says that if tx, ty, and tz is all 0, that means that there is no translational velocity difference between camera and the scene. Okay, there is no translational velocity. That means what? Camera is rotating around itself. Camera is rotating around itself, and there is no translational velocity between the object and the camera. All you have is the rotational component of the speed. In that case, z doesn't have any effect. Z doesn't have any effect. That means that the depth has nothing to do with this equation at all. That means what? If you are using motion to recover the object depths, you need to have some kind of a translational velocity between the camera and the real one scene. Using only the rotational component of the velocity, you cannot get the depth information. So that's interesting. That's interesting, right? Okay, so we are going to analyze this equation by looking at it using these kind of ideas. We will assume that omega is 0, or we are going to assume that tx, ty, tz is 0, and etc. Okay, let's do that maybe. So this translational component, and this is the rotational component, and the rotational component is independent of z. Can you make any analogies between this new finding and the stereo baseline? I think we said something similar in the stereo too. In stereo baseline, we said something that if you do this and this, you can't get a disparity value. You can't get the depth out of that stereo system. So what was it? Do you remember it? It's very similar.
Find disparity isn't correspondence necessary. Do you mean that?
No, I am talking about not the correspondence. I am talking about the geometry of the two cameras. We said that if you place your cameras in that way, you cannot get the disparity. There was one way, there was one position, one configuration of stereo system. If you configure your stereo system that way, there is no way that you can get the disparity out of it.
On the same line, I think.
On the same line? Well, since we have two cameras, the cameras is going to be on the same line anyway.
Yeah.
It is not on the same line, but if the two cameras if their central projections are at the same point, if the baseline is 0, that means what? Between two cameras, there is a rotational difference, but what do we have the parameters for the stereo? We have the rotational component, we have the translational component. If translational component is 0, there is a rotational difference between the cameras. Baseline is 0. If the baseline is 0, there is no disparity, right? If there is no baseline, there is no disparity, there is no stereo. I cannot get any depth. This one is almost the same thing too. If you don't have any translational velocity difference between the camera and the scene, then you will not get any depth information. That doesn't mean that you won't get any motion information. Of course you will. There is rotational component. But there is no depth information. Okay? Since we use the stereo to get the depth information, we said that if there is no translational component, if there is no T between two cameras, forget about Z, forget about depth. And we are arriving the same conclusion here with the motion. That's what we are saying here. Okay, so let's analyze this a little in a more detailed way. Let's assume that R omega is 0. Okay, tell me a case where omega is 0. Say that, okay, give me an example, a camera motion example. Omega is 0, our camera is moving with respect to scene, but our omega is 0 and our Tx, Ty, Tz is not 0. Just give me a real life example.
Can we, there is a camera you say that while they catch runners who come to cross. And it's going only y axis.
It's going on in the y-axis, like it's like the train, right? I have a train. These are the cars on the train. Okay, I have a camera looking towards the side of the train. While the train moves, I am taking the pictures of the nearby scenery of the nearby houses. So there is no x component, there is no z component, there is only y component, right? So there is no rotational component. That's one good example actually. So there is no rotations. If you put a camera looking towards the outside on a train, moving train, then there is no rotational component. And in fact, there is no x and z components either. So that's a good example. So that's one way of doing it. How about if I put a camera in front of a car. My car is moving, okay, forward. I place the camera just on the dashboard, looking through the windshield, the front glass of the camera, okay. Then in that case again there is no rotational component, but there is a translational component. Star field simulation. Do you guys remember that kind of? Okay. Star field simulation. Can I get it? Okay, 1 hour space flight. This is good. Turn off the... Okay. So this is a motion from a camera that you placed in front of your space vehicle, right? There is no rotational component. There is no Tx, there is no Ty, but there is only Tz, right? So I like this one. Why would I? Again, there's a problem with my viewer. I cannot make it full screen, but maybe I can make it. No. Oh, okay. Now it is full screen. 1 full hour of fun. I'm going to make the speed like 2 times more exciting. Okay, so let's look at this motion. As you see, the points near the center, come on. As you see, the points near the center of the image, like Can you see it here? Can you see my mouse cursor? So this point here is very, very slow. This one is very, very slow, right? So, but the points around here is very fast. Near the corners, near the edges of the image are very, very fast. And this point in the center, like here, they are very, very slow. I mean, they seem slow. Do you guys hear me? Do you guys hear me?
Yes, yes.
For some reason, my closed caption stuff doesn't work. I cannot read. Okay, so there is a special point here. I mean, in my image, there is a special point here. Suppose I am trying to find that point, and let's see what happens here. Okay, so I am going to assume that my omega is 0. If omega is 0, this one will go, will go, will go, will go. All I have is this translational component. If omega is 0, all I have is this. Okay, like the other one. And I am going to assume that Tz is not 0. Tz is not 0. Okay, if Tz is not 0, I will have, of course, this equation and this equation for x and y, vx and vy. But I like to find a special point in the center that I showed you. Okay, they say that take this point f times tx over tz. Let's call this x0. Okay, don't ask me why I came up with this one. Let's call this x0 and let's call this y0. Okay, and p0, the point p0 is x0, y0, and f. If I write this equation in terms of x0 and y0, I would write it this way: x minus x0 times tz over z, y minus y0 times tz over z is same as this one. And if you plug these in, okay, instead of x0, put f times tx tz and multiply this one with this one and this one. Tz over z, this one will go over and z will come back, and I will end up with the same equation like that one. Okay, so these two are, and this one and this one are exactly the same if x is like that one. You don't have to worry about tz being 0 because I assume that tz is not 0. So let's look at this equation. What does the equation say? This equation says that your points on the image, if they are very close to x0 and y0, okay, if your points are very close to x0 and y0, that means what? On your image, your vx and vy will be very, very, very, very slow. So we are talking about a special point here, right? So if you are exactly at x0 and y0, you will see your points moving not very, very fast. But if you are away from x0 and y0, you will move very, very, you will move faster. I wouldn't say very, very. Let's go back to that YouTube stuff again. YouTube and star field simulation. I don't know why my YouTube is so slow. I need star field simulation of 1 hour. Okay, this one. Let's go to that one again and okay. So what I am saying here is, let me make this a little bit faster. This space vehicle is so fast, so slow. Make it faster. Okay. So somewhere in the center, that x0 y0 point here, okay, things don't move very fast. I mean, of course the objects are very fast, these stars are moving very very fast in real world, but in my image they are very very slow. Look at this one, it's very very slow. Okay, it's very very slow. This one around here, it is very very slow. But if you move around the near the edge of the image, things get very very fast, much faster than here. So this equation kind of tells you that. Of course, and also this equation tells you that if the objects are far away from you, okay, so how would you say them, fast or slow? If z is very large, Vx would be slow, large or small?
It should be very slow.
If z is very large, then Vx should be and Vy should be very very small, and that's what happens. Okay, so if the star is far away, okay, if the star is far away, they are moving slow. When they get closer and closer, they get brighter. Okay, in that case z gets small and they are much faster. Okay, so let's look at this one. This one is becoming very very close, and they are very, now it is very fast. Okay, they are very very fast if they get slow, closer to us. Okay, so this equation is talking about that, and that p0 is a special point. Okay, there is a point p0 on my image if my omega is 0 and my tz is not 0. Okay, that point is called point of expansion or point of contraction. If tz is greater than 0, it is point of expansion, like this one. If tz is less than 0, it is a point of contraction. Okay, point of contraction. And so this happens when you place your camera in front of your car, and this happens when you place your camera in the rear window of your car or space vehicle. Okay, and this motion is explained like that. Okay, good.
Can I ask something?
Sure.
There was a type of camera which didn't show the image from a planar projection. We were using it for finding the real size of the objects, I think. I don't remember the name of that camera. But with that lens, would this object would seem like as if they are testing?
But you are talking about the telecentric cameras?
Yes.
No, of course, with the telecentric cameras, f doesn't have. With the telecentric cameras, there is no perspective projection. If you don't have the perspective projection, there is no similarity of the triangles. Okay, this equation does not hold. Where is my? This equation does not hold, because with the all you are doing is you are doing the orthographic projection. When you do the orthographic projection like this, okay, the size of the object doesn't change at all. So z doesn't make any difference. So this won't happen. No. By the way, with a space vehicle and a telecentric lens, it doesn't happen at all, because telecentric lenses need very large glasses in front of the glasses, and the most you can see with a telecentric lens is the diameter of the lens. You cannot see larger than that. You cannot see larger than that. I am receiving this. Do you guys see this small booklet? Advanced Optics. Every month they send me their offerings about the lenses, and they talk about the telecentric lenses. Where is my telecentric lens? Let me show you the telecentric lens section in here. Yeah, these are the telecentric illumination solutions. These not the lenses, but the telecentric illumination. It has to be a little bit different because all the light rays has to be parallel in that case. Mechanics lenses, specialty lenses 10 and 11. Come on. I was not going to show you telecentric lenses only. There was a different type of lens, liquid lens. That was a very interesting lens. Transition, promotions, telecentric, better. Yeah, okay. So these are the telecentric lenses. Okay. So these are the telecentric lenses. Telecentric lens sees only the parallel rays. Okay. You don't see anything outside of that parallel area. Okay. It is not like the perspective cameras. With the perspective cameras, that cone gets larger and larger when you look at the infinity. With the telecentric lenses, all you see of the universe is just 3 centimeters high. You won't fit any stars in it. Okay, so that's why the telecentric lens shapes are like that. You cannot see anything larger than that area. And the other thing that I'm going to show you is the liquid lenses. With the liquid lenses, the main component of the lens is not a concrete lens anymore. It's not a rigid glass. It is some kind of a liquid, and you change the structure of that liquid by applying electrical signals. Okay, so when you change the shape of that liquid, it shows different lens effects, and your focal length changes in a matter of milliseconds. So instead of moving something mechanically, you apply electrical signals and you change the shape of the liquid in a matter of milliseconds, and your shape of the lens changes dramatically, and you get the desired effect. They say that this is a very good use for changing very fast, in a very fast way, the effective focal length of your lens, and you can inspect very close by objects or very far away objects in a very efficient way. I think they have, I knew about these liquid lenses, but I didn't know that they produce these kind of robust industrial versions of it. I think I will buy one if I can find the money, and I will test it. That would be interesting. That would be interesting to run some shape from defocus experiments on it. Okay, so no telecentric lenses for your spaceship, Salman. Okay, don't use telecentric lenses in your spaceships. Use your telecentric lenses for inspecting very small objects. Okay, it looks like I'm out of time. Let's take 10 minutes of break. After the break, we will be here. Let's be here 15:39. 10 minutes of break. Muhtemelen ben bir arayıp bulayım onu. Yani bulsan da bir şey fark etmeyecek. Orada o fen bilimleriyle şey aynı olacak. Yani hocam onda ben önde var 4 tane geldi. 5.'sini rektörlük üzerine yollamışlar ya.
Evet, bitti mi?
Evet.
Arkası da bu kullanılamaz. Yani.
Bak burada da var. Bu da red sebepleri. Red sebeplerine cevap da yazdık biz. Onları üst üste
Peki makul mantıklı bir şey mi?
Yok canım. Okumamış ki. Adam diyor ki yükseklik verisini nasıl üretiyorsunuz ben anlamadım diyor.
Yükseklik verisini üretmiyorsunuz değil mi siz?
Yok yükseklik verisini satın alıp kullanıyoruz biz. Ve bu işin orijinalliği de diyoruz yükseklik verisini kullanmasıdır diyoruz. Şimdi adama ben buraya bu projeyi okumayıp da reddedeni ne yapayım diye mi küfür etmeliyim? Yani
Sanırım anlaşıldığı üzere
projeyi okumamışlar yazacağım abi. Projenin
karar vermiş
yazacağım.
olan şeyimiz.
Yani bana gönderilen gerekçelerin, net gerekçelerin ya projenin anlaşılmamasından ya da okunmamasından kaynaklandığı anlaşılmış. Yazdım ben oraya.
Yazıp gönder. Bu kadar
O
basit.
sebebini yaptım. Aha burada yazıyor. Buradan 3 tane ok giriyor. Yükseklik, radar ve 2 boyutlu görüntü giriyor buradan. Buradan da geminin konumu çıkıyor. Bu adam yüksekliği nereden uydurmuş anlamı?
Onun işte yüksekliği satın alıyoruz. Deniz seviyesinde de yüksekliği
Bu kararın yüksekliği lazım hocam. Hani radar kenar boyunca arkada daha bakmadan bir ilgi yapmadan gelmiyor ya. Bana da ne lazım biliyor musun? Ben ne lazım ya? Efendim İlhan? Tamam oldu. Ha dersteyim, hadi görüşürüz. Okay. Let's continue our experiments with this nice set of equations. We assume that omega is 0, and then we assume that Tz is not 0. So what is Tz is not 0? It means that there is a component of the camera velocity towards the scene or away from the scene. Okay. Remember our first example? We said that, let's say we have a camera looking through the window of a train. It is looking at the side views of the train. Let's try to see what happens if our case is like that. Again, omega is 0, and this time Tz is going to be 0. When Tz is going to 0, when Tz is 0, in that case, this point doesn't make any sense, because if Tz is 0, these are 0, and I won't find any x zeros or y zeros. Or if I find it, they will be at the infinity. So there will be no point of contraction or point of expansion. Okay, so those points will not be visible, or at least they will be at the infinity. Okay, so if omega is 0, okay, if omega is 0, if Tz is 0 too, then this will go away, this will go away. I will end up with Vx is going to be minus f times Tx over z. Vy is going to be minus f times Ty over z. So what does that mean? It means that if the object is away from V, okay, if z is large, then Vx is going to be large. If z is large, Vy is going to be large. Okay, so my x and y speeds on the image will depend on the speed of the camera. Also, the translational speed, relative translational speed difference between camera and the real world itself, plus the depth of the point. If the point is away from me, then in that case I will see it very, very slow on my image. If point is close to me, z is small, then I will see its vectors as very large. Okay, so the motion field vectors are parallel to each other and inversely proportional to depth. Inversely proportional to depth. They will be all parallel. They will be all parallel in this case. Well, in this case, it looks like all the Vy's are 0. All the Vy's are 0. That YouTube is messing everything up. Let me close it. Is this better? No. I think I can manage it. Okay. So in this example, Vy's are all zeros, but if Vy's are not zeros, then you would get something like this. Closer the point, something else is happening, I don't know. Closer the point, larger the motion field. Okay. So this is what we have seen so far. If Tz is not 0, our motion field is radial. It is radial around a P0 point. Okay. If Tz is 0, the motion field is parallel. Okay. As you see, the motion field is parallel here, and in this case, the motion field is radial. Okay, so the center of the this radial structure is point P0. Okay, good. So we looked at the omega 0 case, and let's look at this general analysis with the pure translation where omega is 0. Okay, we have a vanishing point, focus of expansion or contraction. Okay, and with the translation we can make guesses about z, like this one. I know that the z components of these large motion fields are small, they are closer to me, and z components of these small motion fields are large, they are away from me. So this pure translation gives me lots of information about depths of points. In fact, this is the formula for this case. The z of a given point is given by this formula. The speed of object in the real world times f divided by speed of the object on the image. Okay, so with the pure translation I can get all that information. For the pure rotation where omega is not 0, we did not study this. It doesn't carry any 3D information, as we said before. Okay, and the motion field becomes a quadratic polynomial in image, and it is basically used for mosaicing or making a panorama of an image. Okay, so this one doesn't carry any depth information. This is not good motion for recovering the structure of the scenes. If we have a moving plane, again we didn't study this either. Okay, motion field is a quadratic polynomial in image, and it is good for mosaicing for planar scenes, and usually you use this technique to produce the mosaics of the Earth surface or the Martian surface. Okay, because the satellites around the moon or Earth or Mars are taking these kind of images. There is this rotational component of the satellite and the translational component of the satellite, and it sees the surface of the Mars or Earth as a plane, as at least a partial plane. To put them together, okay, you are using this motion field information. Okay, we didn't see this either, so I am not going to go into details of those. Okay, so these are the two things. These are the two or three things that I am going to tell you about these two equations, translational component and rotational component. And it is important to know that translational component only contributes to the depth estimation, not the rotational component. Rotational component is good for producing panoramas or the mosaics from the motion. Okay, so far we talked about the motion field. That's good, motion field. We talked about motion field. But we didn't talk much about how to get this motion field from the images, from the video sequences. Okay, so what we have assumed that we come from the other side. We said that okay, these are our equations. If we know that there is no rotational component, then we will end up this and such and such. So we didn't talk much about the images. Let's talk about the images. Let's talk about the images and to get the motion field, how we do that. And we are going to call it optical flow, and you are going to see why we are calling it optical flow. Motion field estimation. Okay, what is the motion field? Again, motion field is the, let's say this is my V and this is my image, and if I do this is going to be small v. Okay, motion field is the projection of the real world velocity vectors on the image plane. That's what we said. Okay, so getting this v exactly from the projections is not possible because in the real world you cannot see these vectors, right? I cannot see these vectors. I only assume that there is a vector between this point A and A prime. That's what I assume. Since these vectors do not exist in the real world, I cannot project them on my image plane. I don't know. So there must be a way of estimating it. Okay? We cannot estimate the motion field directly. Instead, we are going to estimate this optical flow. Optical flow is this. I am going to try to track the brightness patterns on the images. Okay? There is a pattern, a brightness pattern. I am going to check to see where that brightness pattern went in my next frame. It's like I detected the corner, and I am going to detect another corner in the next image, and I am going to see where that corner went, something like that. But this would be a very dense, this would be a very sparse way of estimating the motion field. Instead of doing that, I like to do this for every point in my image. Very, very dense, very, very dense, very, very dense motion field estimation. And that's why I'm going to call it optical flow, because instead of estimating the real motion field vectors, I am going to estimate where those brightness are moving. This is the best I can do. The alternative is not possible. And we are going to call it optical flow. And optical flow will be assumed to be similar to motion field. But before we start, we should know that optical flow and motion field are not the same thing. Let's look at this example. Let's say I have a wooden sphere. Okay, very it's not a shiny sphere. Okay, it is wooden, and I am spinning it very fast. I am spinning it very fast. I am taking images of it, one after the other. So what would you see as difference? If you take the image of a very fast spinning sphere like this, what kind of differences would you see from frame number F number 1 to F number 2? I bet you would see exactly the same image like this, right? No difference. The sphere is spinning very fast, and even if it's spinning very slow, I cannot see any difference between two frames. Frame number 1 and frame number 2 are exactly the same, even though the points are moving. Even though I know that this point moves to this point, and this point moves to this point. I know that, but in the image everything seems to stay in place. So my optical flow, which is the estimation of the movement of the patterns, brightness patterns, will tell me that nothing is changing, but in fact motion field is changing. In this case, motion field will not be equal to optic flow. Okay, so we are trying to tell you that optical flow and the motion field are not always exactly the same thing. Okay, this is one example. Another example is this. Let's say this time I have a smooth specular uniform sphere. It's a metal sphere. Its metal is shiny. Okay, and the sphere doesn't move at all. It doesn't spin, it doesn't move. It is stationary. Okay, there is a light source. When I shine this light source, I will get a reflection from this part of the sphere, right? I took an image number 1, and I moved my light source to other side. I took another image, and it is there now shining. So if I take these two images, the pattern has moved from this location to that location, right? So if optical flow is the tracking of the brightness patterns, this optical flow will tell me that this part of the sphere is moving. But in fact, nothing is moving. My motion field is all stationary, but optic flow is giving me something else. Again, in this case, these two things are different. So what can I do? I am not going to do much. I will assume that motion field and optic flow are the same thing. And I will say that don't do this, okay? Don't change the light source on your scene. Keep the light source the same. And don't try to use the optic flow on these kind of objects, okay? And that's going to be bad for me. And if I stay within these constraints, then you may assume that optic flow vectors and the motion field vectors are going to be the same. That's what we are going to do. Okay? Keeping in mind that optic flow is not the same as the motion field, we will assume that the apparent brightness of moving objects remain constant. Okay? The alternative is estimating the MF directly, which is not possible. I cannot take pictures of velocity vectors in the real world because there is no velocity vector in the real world. There is no visual velocity field in the real world, of course. Okay, so that's what we are assuming. That's what we are assuming. Okay, good. All right, so we will come back to brightnesses. We will come back to images, and I am going to take some derivative with respect to x, y, and z, and we will come up with some equations that will let us estimate the optic flow in a dense way. Okay, so these are our assumptions. Let's say in a 3D world, okay, I have a point P. This point P is moving in three-dimensional world, just a single point, okay? And these three functions, xt, yt, and zt, okay, these three functions, xt, yt, and zt, are the coordinates of this point in x, y, and z. You may ask, how can you get these coordinates for a p, but don't ask yet, okay? Those are our assumptions. Okay, those are assumptions. Again, this is the x, y, and z component of the real world P. The projection of that point on our image are x and y, xt and yt. Okay, xt and yt, those are the projections. So this is a two-dimensional image point. This is a three-dimensional real world point. Okay, two-dimensional image point. And I have a function e that is going to tell me the brightness of that point. Okay, since P is the same point in the real world, wherever it moves under the same light, I should be getting the same intensity for that point. Okay. So that's what I'm saying. So E is a function that gives me the brightness of that P. So maybe we can show it this way. That point will be at this point at time 0. At time t1, it's going to be at this point at time 1. Okay. Anywhere between time 0 and time 1 is going to follow some kind of a trajectory. But wherever it moves, it should give me the same intensity because the object is not changing. The light is not changing. Okay, its intensity should be the same. And this function is going to give me that brightness. Okay. So I have this real world point P, its image on the image coordinate system, and this is the brightness of that point. Okay. So the idea is this. Okay. This is in the real world. Okay. That point is moving in the x, y, and t dimension. Okay. So this E is like a three-dimensional image. At time t0, it is here. At time tk, it is here. In between, it moves in this three-dimensional world. Wherever I move, doesn't matter on this red trajectory, it's going to give me the exact same brightness. Since exact same brightness stays the same, if I take the derivative of that function with respect to time, I should get a value of 0 because it is not changing. It remains constant. Okay? This is called brightness constancy assumption and brightness constancy equation. Okay? This is called brightness constancy equation or brightness. And the assumptions that we are taking here are brightness constancy assumptions. Did you get this right? I mean, it's kind of important to understand the rest of the optical flow algorithm. All I am here saying is that the point P is moving in a three-dimensional world. It is following these three trajectories, x, y, z. The image of that point on my image, okay, the image of that point on my image frame itself will follow this trajectory. Okay, I know that too. And wherever I look at that trajectory, the brightness of that point should be exactly the same. It should not change. Since there is a constancy, okay, if I take the derivative of this E with respect to t, it will stay constant, so it should be 0. That's what I am assuming. Question. Salman, question for you. Okay. How do you take the derivative of a function like this with respect to x? I like to take the derivative of f with respect to x.
Change.
So what would you do?
So the f over dg and dg over
yeah, like and the g over dx, like that, right? So I'm going to do it with this one too. How do you take derivative of such a thing, okay, with respect to t? Now I have 1, 2, 3 things, and if I had f gx, okay, and hx. And if I like to take the derivative of this thing with respect to x, then I would put a plus sign here and I would do it with the h, right? That's what I'm going to do. Let's see. Okay, so let's take this delta derivative of e with respect to derivative of, like that, okay, times plus respect to y, and this one plus this and this equal to 0. Good. Okay. So let's look at this equation. Let's try to see the things that we already know. What is this? This is a new thing. Change of x with respect to t. So it is the speed on the x component of that point, right? So this is vx, right? So this is vy. So the speed of that point that we are tracking with respect to x on the image, and speed of that, velocity of that point on the image with respect to y. I know that one. How about this one? What is this? Change of the brightness with respect to x. What is that?
I think we call this. I don't know what we call, but we use this in corner.
I know that, but I don't know the name. It starts with a G. GR. If we show it with this IX, it is the image gradient with respect in the x dimension.
Yeah.
Plus this is y. Okay. Image gradient with respect to x, image gradient with respect to y, plus ET, image gradient with respect to t, is equal to 0. Okay. So brightness constancy equation gave me this. So what do we have now? I have, let's say, 10 frames, like that. T0 to T10. Okay, I have 10 frames from T0 to T10. And I like to calculate the Vx, Vy of each point for all the frames. Okay, it looks like I can do that. I mean, calculating the x gradient and y gradient for a point. Let's look at this one. This is T0. This is T1. For this point, calculating the x gradient and y gradient is okay. So I can get this. I can calculate this one. I can calculate this one. I don't know this one or this one. That's okay, because I like to find them. I mean, I need to find where this point is going, like that. Okay, that's the optical flow. So I can calculate this Ix and Iy, no problem. I need to calculate this one and that one. And how about this one? Can I calculate this one? How does the brightness change with respect to time? Of course, why not? Because I know this point, I know the brightness of this point. If I take the difference between these points, that will give me the brightness derivative with respect to time. So I can calculate this one too. So do I have everything that I need to find these two values, Vx and Vy?
Didn't we assume the brightness stays the constant? So
Brightness constancy is assumed, but that brightness constancy is for on this red trajectory. Okay, on that red trajectory, brightness stays the same on that red trajectory only. Image gradient at this position, x and y, they can change, of course. And that for that point, ET, okay, the brightness of that point, xy point, on the image, of course, that can change too. Okay. So I have an equation on Vx and Vy. I have an equation on Vx and Vy. And I know this value, I know this value, I know this value. It looks like I know an equation, but I have two unknowns. I know an equation, but I have only two unknowns. Okay, let me try to write this in a more mathematically explainable way. So this is a Ix and Iy. Ix and Iy, I can write it. I could write it if I can. That YouTube thing just messed everything up. But that was a good simulation. Ix and Iy as a vector. I wrote it. And then Vx and Vy, okay, it's a vector, is equal to minus Et. Okay, so it's a inner product of two vectors is equal to minus Et. It's a scalar. So I have a vector, two components, but I have only a single equation. So this is basically measuring. This is my gradient vector, right? If my velocity vector is perfectly aligned with the gradient vector, okay, then I can say that I know my velocity vector if they are perfectly aligned, something like this. Okay, let's say if this is my gradient, image gradient vector, okay, and if this is my velocity vector v, okay, when I do the dot product between these two vectors, all I am measuring is the projection of that vector on this intensity vector. Okay, all I am measuring is just this component. But by coincidence, if my V and if my image gradient are perfectly aligned, then I can perfectly find V. And if I am not that lucky, if my intensity gradient is like this, and if my velocity vector is like that, then there is no way that I can get anything. Out of this. I will not get anything for this V, because their product will produce 0, and I cannot find anything. Okay, so this brightness constancy equation gave me only some part of my V, only some part of my V. Okay, and maybe I can explain this a little bit further using the slides from the book or somewhere else, I don't know. Okay, so I already said that. Okay, this is what we get. This is our gradient, this is our velocity optical flow vector, and this is the derivative across the frames. And if I put them together, I get this and I get this. So I have two unknowns and I have a single equation. That's not enough for me to calculate all that stuff. So some people are doing this. Some people are doing this. They say that if a given image like that, okay, if I try to estimate the velocity of a single point for a neighborhood, then the nearby pixels should have similar velocities, right? So why don't I calculate the velocity vectors of all the neighboring pixels? Since they have similar velocities, then I will have many equations, and those equations will come together and will form a nice linear equation. How about this idea? I mean, look at this one. Look at this one. Let's say for this pixel, this green is the velocity vector. For this one, green is the velocity vector. They all similar to each other, right? And let's assume that they are all the same. They are all the same. They are all the same. If I all put them together, and if I write 10 equations one after the other, I will have 10 equations and single unknown. Okay, two unknowns, Vx and Vy. And I will solve this problem altogether. Is this a good idea?
It's a good idea, but I think it's only can work while biz sabit hızdayken çalışır diye düşünüyorum ben hocam. Yani. Sanki sabit hızla bir ivme hareket olduğu zaman çalışmaz gibi yani.
Well, what you are saying is, I mean, whatever your concerns are, I think your concerns should be valid for any kind of movement. I mean, your concern is not about using the neighborhoods. Oh, you are saying that, okay. You are saying that if the neighbors have different velocity vectors, then we are in trouble. That's what you are saying. Well, you may assume that they have all the same vectors. The problem with this picture is this. Remember, if my image gradient and V are perpendicular to each other, their multiplication will be 0. Okay, their multiplication will be 0, and I will not get anything for V. Okay, V is not 0, their multiplication is 0. Since all of them have almost the same V, okay, whatever you do, they will all end up with 0, so you won't get anything out of it. So this idea will not work for all the cases, but it's going to help us. It's going to help us to find the optic flow vectors. Okay, so this brightness constancy equation is nice, but it will not produce us the optic flow vectors for all the cases, and I am going to show you why in a few minutes. How should I do that? No, this is not good. Can I? Okay, let me try to draw it myself, in whatever minutes I have left. Let's say I have a circle like this. I have a circle like that. Does it work? Does it work? Yeah, I think it would work. It doesn't work for some reason. Okay, let's say I have a circle. I need to be very careful. Okay, can I move that around? Yeah, I can do that, right? Okay, and then I have a rectangle like this. But the thing is that I want to make this rectangle behind this circle. Okay, delete it and draw the circle again. Okay. Okay, good. No, not good. I cannot touch it now. Can I select it, the other? Can I select the other one? The other circle? No. I think I will stop at this point and my time is up. We will continue next week on this one. And finish up this chapter and start the next chapter. Okay? I was going to show you when it is okay to have optical flow, right? And when it doesn't work. And I was going to connect it with this gradient and velocity vectors and their angles. Okay, we will continue at this point. Today I am going to give you your second and third homeworks, and during the finals time you are going to get your fourth homework. Okay. Okay, I'll see you tomorrow. I will see you next week. Bye. Are there any questions? Maybe I can answer a few quick questions. Any questions? Okay, I'll see you next week then.
Thank you.
Thank you.
Bye.